Good morning, everyone, and welcome to this second day of the Eyes on Earth Roadshow. It's an online version. We were planning to have it in Zagreb, but due to COVID-19, it's online. But we're happy you're there. My name is Martijn Seiger, and I am the consortium lead of the Eyes on Earth project. Yesterday, we shared a lot of information on the Copernicus system and services. This session is in collaboration with the Copernicus Research and User Support Office. In this session, an introduction is given to Sentinel 5P data. The demonstration is given by Mr. Miguel Castro Gómez, remote sensing specialist. You have the availability or opportunity to ask questions during the presentation, which will then be answered by the specialists. And I will join you again at 12:30 when this session ends. And then I want to invite you for the following sessions of the Eyes on Earth Roadshow program. Miguel, I would like to give the floor to you. Thanks a lot and enjoy the session. Thank you.
Okay, thank you, Martin. And let me just start the exercise.
Hello, everybody, and welcome to this RUS Copernicus training session. My name is Miguel Castro, and today I will be guiding you through this exercise in which we will use Sentinel 5P data to monitor air pollution over Spain. Before starting, let me tell you the objectives of this session. You will learn two main things. First, how to monitor pollution with Sentinel 5P data, and second, what is the RUS Copernicus service and how it can help you in your projects with Copernicus data. Before starting, let me tell you that, as you may already know, we are going to run this exercise using Python, so it might be a little bit different from previous RUS training events that you might have seen or not. Okay, so let's get started. And the first thing I want to show you is the outline I will follow in this training session. So first of all, I will, as I said, introduce you to the RUS Copernicus service so that you have a better idea of how this project can help you in your projects with Copernicus data. Then we will have a look to the Sentinel 5P mission, understand a little bit more its characteristics, the details, the products that are available so that we can better understand the potential applications that can be run with this Sentinel mission. And then we will move into the RUS Copernicus virtual machine where I will run the exercise and explain you all the steps. At the very end, we will save some time for a Q&A session. So if you have questions during the exercise, please feel free to send them as soon as possible. The complete duration of this training should be around 1.5 hours. So let's get started and let me introduce you the RUS Copernicus service. So first of all, RUS stands for Research and User Support for Sentinel Core Products. It is an initiative founded by the European Commission and managed by ESA with the objective to promote the uptake of Copernicus Sentinel data and support R&D activities. The service provides a free and open scalable platform in a powerful computing environment, hosting a suite of open source toolboxes, which are pre-installed on virtual machines. This will allow you to handle and process the data derived from the Sentinel satellites. So what does that mean in other words? Well, with the large amount of data produced by the Sentinel satellites nowadays, the challenge in Earth observation is no longer data availability, but rather storage and processing capacity. So to solve that, RUS Copernicus offers virtual machines so that you have the appropriate computing environment to handle the data. In addition to all that, RUS also provides specialized user help desk to support your remote sensing activities with Sentinel data and a dedicated training program such as the training activity we are doing today. So as you may already know, you can find all the information about the project and how to register on our website. So I recommend you, if you don't know them already, to check after this training session to get familiar with the service and see the different VMs we have, the list of software that is included, and so on. And finally, I want to introduce you to our YouTube channel, in which we put the exercises that we do. We organize webinars every month, and the recorded versions all go to the YouTube channel as well as to the RUS training website. So if you're interested in more applications with Sentinel data, this might be a good starting point. Okay, so knowing already what is the RUS Copernicus project, let's move on and talk a little bit more in detail about Sentinel 5P. So Sentinel-5 Precursor, or Sentinel-5P, is the first Copernicus mission dedicated to monitor our atmosphere. The satellite maps a multitude of air pollutants around the globe. It was launched in 2017. Sentinel-5P reached its routine operations phase in early 2019. It aims to fill the data gap and provide data continuity between the retirement of the previous Envisat satellite, the NASA's Aura mission, and the launch of the upcoming Sentinel-5 satellite. Sentinel-5P carries the state-of-the-art Tropomi instrument to map a multitude of trace gases. Some details about the technical characteristics of the mission that I want to share with you. Well, in this occasion, we have a single satellite mission. If you compare this to Sentinel-1, Sentinel-2, or Sentinel-3, in which we have two twin satellites orbiting at each other at 180 degrees at each other. In this case, we only have one single satellite with a swath of 2,600 kilometers. It has a global daily revisit time and a spatial resolution of 7 by 3.5 kilometers. And just a few comments on its orbit. It follows a polar sun-synchronous orbit in loose formation with the Suomi NPP mission from NOAA. Loose formation here means that Sentinel-5P orbits few minutes behind Suomi NPP, and the reason for that is that Suomi provides a collocated high-resolution cloud mask, which is important to derive some of the level 2 products that are available via Sentinel-5P. So let's now talk about the instrument carried by Sentinel-5P. As I said, it is known as Tropomi, which stands for Tropospheric Monitoring Instrument. And what sets this instrument apart from previous sensors is that it measures in the ultraviolet and visible, near-infrared, and shortwave infrared spectral bands. This means that a wide range of pollutants such as nitrogen dioxide, ozone, formaldehyde, sulfur dioxide, carbon monoxide, and more can be imaged more accurately than ever before. So let's move to the different data products now that are produced by Sentinel-5P, and let's have a look. So data products from Sentinel-5P Tropomi instrument are distributed to users at two different levels. The first one, the one you can see on the slide, is known as level 1B, and it provides geolocated and radiometrically corrected top of the atmosphere irradiance in all spectral bands, as well as solar irradiance, and this is very important, the main input for the level 2 products, for the level 2 processor. So on one hand, we have level 1B. This should be the product of interest if you are looking for the actual measurement done by the sensor. On the other hand, we have level 2. Level 2 provides atmospheric geophysical parameters. So this is the product type most of you as regular users would be interested on. And is of course the level that we will be using in this training session. So in this list, you can see the details of the different level 2 products that are available. With Sentinel-5P, you can see their acronym that it's used and just a short description of the meaning. So you can see we have several products for ozone, then we have the one for NO2, well, and you can see the list by yourself. So finally, the last technical aspect I want to share with you about this mission is the timeliness of the data. In this regard, we can distinguish three options in which the data is made available to users. The first one is the near real-time or NRT timeliness, and this is mainly to be in line with the needs of numerical forecasting systems, and it only applies to level 2 products, which are to be supplied within 3 hours after sensing. So in near real-time, you will not find level 1B, you will not find the actual measurement done by the satellite, but only the geophysical parameters. Then we have a second level in terms of timeliness, which is known as offline, or non-time critical. So the offline products take advantage of increased accuracies achievable when specific calibration steps and trace gas retrievals are performed with relaxed timing. So in this case, it applies both for level 1B, which is made available to users after 12 hours after sensing, and then it also applies to level 2 products, which are made available to users 5 days after sensing. The main difference between an offline level 2 product and near real-time level 2 product is, apart from its increased accuracy, is that the offline level 2 product will be the full orbit of the satellite, while the near real-time product will be just a tile of the orbit that the satellite was following. Don't worry if this is new for you. We will actually see this difference in the exercise later on. Okay, so the third level in terms of timeliness is known as reprocessing. And this is just a level that is used whenever a major update in the processors is made. So whenever ESA decides to upgrade the processing baseline to improve the accuracy of the data, then we might have a reprocessing of the dataset. But this has no time constraint and is only done when required. Okay, so let's move on. And now let me give you a brief introduction about the naming convention used by Sentinel-5P. I can imagine that you are already familiar with Sentinel-1, Sentinel-2, or Sentinel-3 data, but maybe not with Sentinel-5P, or maybe it's the first time you are working with Copernicus data. You have to know that in the Copernicus environment, let's say all the Sentinel products follow a standard naming convention. And the name of the products are actually very important since they contain already information that can be used to process your data. So here I have a typical, I have one product, a level 2 NO2 product, and let's split the name into the different parts and let's have a look. So the first thing we see in red is the mission name, in this case Sentinel-5P, it will always be that. Then we have the processing stream, so here we make reference to the timeliness of the product. Is it a near real time or offline or reprocessing? So you can see there on the slide the different options. Then we have its processing level, either level 1B or level 2, you know already from the previous slides. Then we have the product identifier. So remember, if it's a level 2 product, we have different geophysical parameters. So we have a product for NO2, we have a product for carbon monoxide, and so on. So here you can see the full list for the level 2 products. I'm not including the level 1B, just to focus on the data we will be using today. And then this is followed by the start and end of the granule. So this is in UTC, and it gives us the sensing time in year, month, day, and then followed by hour, minutes, and seconds. Then we have the orbit number, which might be relevant for you, the collection number, and the processing, the version of the processor that was used to process this data. Those are parameters that most likely are not that relevant as the previous ones, but it still is good to know. And finally, at the very end, we have again a time information, which is in this case, the time of processing for this granule, the time in which this granule was ingested, and follows again the same structure in terms of timing. So year, month, day, etc. Okay, so with that clear, let me introduce you a little bit more the specific level 2 product we will be using today. In this slide, you can see the full list of level 2 products available from Sentinel-5P. And as you can see highlighted in green, in this exercise, we are going to use level 2 NO2 products. So let me give you some insights regarding level 2 products. Well, first of all, you need to know that Sentinel-5P products are delivered as netcdf files. And it is important to understand at least the basics of this format. netcdf stands for Network Common Data Form and is a file format for storing multidimensional scientific data, such as, for example, temperature, humidity, pressure, wind speed, and in the case of Sentinel-5P, concentration of a specific gas. Each of these scientific data or each of these variables can be displayed throughout a dimension such as time. And this format is widely used in some scientific domains such as atmospheric or the oceanographic community. So as you can see on the slide, some of the main characteristics, and there are many more, but some of the main ones to know about netcdf files is that they are self-describing, portable, and scalable. So you can see there the description of that. Of course, if you're interested to know more about netcdf files, just check on the internet and you can see the full list of characteristics and details about this data format. So knowing that, it is very important to properly exploit Sentinel-5P data and understand how netcdf files are organized is also a key part. So let me give you an introduction to this. So in netcdf files, you can find 4 main let's say, divisions. We have the dimensions of the file, the variables, the attributes, and the coordinates. So I want to introduce you mainly, well, you can see it on the slide, but let me give you a brief summary of variables and attributes. The variables in a netcdf file is the main, is where we will find the actual measurement. A variable represents an array of values of the same type. And as I said, variables are used to store the bulk of the data in a netcdf file. So it is in a netcdf variable where we will find the measurement, in this case of Sentinel 5P. Then another aspect I want to mention are the attributes. So netcdf attributes are used to store ancillary data or metadata. And most attributes provide information about a specific variable. But on the other hand, we can also have attributes that provide information about the entire netcdf file, and those are called global attributes. Well, don't worry if this is very new to you. During the exercise, while we process the data, I will come back to these concepts so that you can better understand their definition and so on. Okay, so let's move on, and now let me give you a little bit more of information about the actual structure of the netcdf files we will be using today. So remember, we are using level 2 NO2 products, and as you can see on the slide, on the left side, we can see how the netcdf file is arranged. So at the root level, as you can see in pink, we have the global attributes. So those are metadata information that is linked to the file itself and that is relevant. Then the file is structured into groups. We have the product group and the metadata. As you can imagine, the metadata group contains metadata information, and the product group is actually where we will find the main variables. So let me give you a brief overview of the product group. The variables in this group will answer to the questions what, when, where, and how well. So this group stores the main data fields of the product, including the precision of the main parameters, the latitude, the longitude, and variables to determine the observation time and dimension needed for the data. In addition, you will find the QA value parameter, which is very important here and summarizes the processing flags into a continuous value, giving a quality percentage for every pixel that ranges from 100% to 0%. And 0% means complete failure of the pixel in terms of quality, and 100%, as you can imagine, means great quality. Okay, so if you want to know more about the structure of the level 2 products, and if you want to know more about the meaning of every metadata and to really see the details of the product, I recommend you, and I think it's mandatory if you really want to master Sentinel 5P data, I recommend you to check the technical documentation that is made available by ESA and its partners about the different products. In this case, I'm showing you the product user manual of the nitrogen dioxide level 2 product. Of course, there are other technical documents for this specific product and many more technical documentation about the data. So if you are interested into using Sentinel 5P data for your applications, I recommend you to make sure you check those documents. You will find a lot of information there that is very useful. Okay, so let's get started, and now let's move on into the exercise. But before that, I want to introduce you actually the objective of the exercise. Well, our objective today is going to be, as you can see on the slide, to assess the decrease of air pollution caused by the lockdown in Spain due to the COVID-19 outbreak. And we will do so by analyzing the NO2 average concentrations in March 2020 compared to March 2019. Actually, we will use the data set from the 15th of March 2020 until the end of March 2020, and the same in March 2019, just to be online with the lockdown that was established in Spain due to this situation. Okay, so how are we going to do that? Well, we will be using a RUS Copernicus virtual machine, as you know, and within the virtual machine, we will use an Anaconda environment, which will use a Python and a Jupyter notebook to run the analysis. More in detail, within Python, we will be using two main libraries. One that is called Xarray, that will allow us to handle netcdf files in Python, and one that's called HARP. HARP is actually a part of the ESA atmospheric toolbox. So let me introduce you now to the software. So when processing Sentinel 5P data, you have different options, different processing tools that are available in the RUS Copernicus VM. First of all, if you are not familiar with the programming environment, or if you prefer to use a graphical interface, I would recommend you to check the ESA atmospheric toolbox. As you can see on the slide, it provides scientists with tools for ingesting and processing data, such as the one coming from Sentinel 5P. And the important thing to know here is that the ESA atmospheric toolbox is formed by three main components, which are standalone softwares and are known as CODA, HARP, and VISAN. So more in details, HARP is the software that we will be using today to process our Sentinel 5P data from its level 2 to a new level that's known as level 3. So don't worry, I will give you more information about this during the exercise, but just so that you can understand why we are using some softwares. So this is one of the options you have. And by the way, if you want to know how to use HARP in a graphical way and not in a programming environment, I recommend you to check one of our previous RUS Copernicus training sessions. In this case, it was a webinar in which we used HARP and VISAN and the ESA atmospheric toolbox to derive air quality parameters around the globe. Okay, so just a side note. Okay, another option you have apart from the ESA atmospheric toolbox is the Panoply software, which is also very well known and very well documented. It comes from NASA, and it also allows you to handle NetCDF files such as the ones from Sentinel 5P. Okay, if we now move into programming environments, I want to give you here a few options, both for Python and R, which I think are some of the main programming languages used for this kind of analysis. In Python, as I said, we will be using the Xarray library, but there are also the NetCDF4 library, which is very well known, and the IRIS package, for example. In R, we have also dedicated packages for NetCDF files. You can see that the NCDF or NCDF4 packages, of course, the raster package, which is very well known in R, or a dedicated one for NetCDF known as RNetCDF. Okay, so just a brief summary with some references in case you are into this kind of way of working. Okay, so now let me give you an overview of the exercise and how we are going to do it. Well, first of all, what I want to show you is, or what I will show you during the exercise is how to download Sentinel 5P data from the Copernicus Open Access Hub. Then I will give you a very basic introduction to Python and Jupyter for those of you that don't know what Jupyter is and what Anaconda is and so on, just to put a little bit of basic information around. And then I have divided the exercise in two main points. The first one, which is point number 3, is the part of the exercise in which I will show you how to handle a single Sentinel 5P data in Python and how to do some basic operations such as exploring the file, accessing some variables, and do some very basic and relevant processing operations such as the quality filter or a geographical subset. In the second part of the exercise, point 4, is where we will actually run the analysis of pollution over Spain due to the COVID outbreak. In this case, we will use HARP to move our data from level 2 to level 3, and we will see later what does that mean. And then we will use Xarray to manipulate the output of that and derive our final results. Okay, so let's get started, and let me now go to my virtual machine. So I have it here. I'm just gonna go full screen to have a better visibility. Okay, so since you have registered for this RUS Copernicus training, you have received in advance a link to the RUS virtual machine, and on that email you have received also the username and the password. So once you are repeating this exercise, I ask you to access the virtual machine so that you can start the exercise. So I'm just going to put my credentials here and access the environment. Okay, so here I am in the RUS Copernicus virtual machine. And if this is the first time you work with a virtual machine, let me introduce it to you. Virtual machines, or in the case of the RUS Copernicus virtual machines, are cloud-based. And actually, if you are new to cloud computing, I would say this is a very easy way and a very easy step to make to go into the cloud computing way of working, let's say. So as you can see, it looks like a regular computer. We have the predefined list of software that comes already installed in the RUS VM. So you see we have Snap to process Sentinel 1 or 2 data. We have RStudio, we have QGIS, and so on. As you can see, most of the software you need to process Copernicus data is already there and ready to use. In addition to that, we have, as in a regular computer, our dedicated internet browser to just navigate and do our things. But also we have a file manager that we can use to navigate around the VM and save our files and so on. So with the introduction being done, let me now show you how to download Sentinel 5P data. Well, the first thing you have to do is to go to the Copernicus Open Access Hub, which is this website here, which is, remember, the official access point to Copernicus data. So within the Copernicus Open Access Hub, since we are looking for Sentinel 5P data, we have to go to the Sentinel 5P Pre-Operations Hub. Do not confuse the fact that the data is in the Sentinel 5P Pre-Operations Hub with the fact that the mission is already in an operational phase. So this is just a mismatch between the operational phase of the mission and the hub that we are using to put the data. So do not think that because the data is in the pre-ops hub, the mission is not yet operational. It is, and that's how it is. Okay, so once we are in the Sentinel 5P pre-operations hub, as you can see, we have we have basically the same interface as the one you would have if you are in the regular hub for Sentinel 1, 2, or 3 data. So the first thing we have to do to download data, as with the other Sentinel missions, is to define our region of interest. In this case, we are interested in Spain. We are interested in running our exercise over Spain. So we have to define the region of interest. And for that, I'm just going to select the drawing mode in the hub, and I'm just going to run my region of interest covering Spain. I'm not covering the Canary Islands and so on. I'm just focusing on the mainland, just as a side note. Okay, so once we have our region of interest, as always, we have to set our parameters to run our search. And this is done by accessing the advanced menu here in this icon on the upper left corner. So if I click here, the first thing we have to do is to set our sensing period, from when to when we want our images to be. Remember, we said we want to compare mid-March or the second half of March 2020 with the second half of March 2019 to see the effect of the lockdown in error quality. So let's do so. I'm going to show you how to do the data retrieval for 2020, but as you can imagine, the same applies for 2019. So I'm just going to March, just going down, and then I will start my analysis on the 15th, and I will end it on the 31st of March. Once this is done, check the Sentinel 5P mission checkbox to say that you want to look for Sentinel 5P data. This is kind of obvious, but you have to do it. And then out of the 4 parameters we have here, the only one we are going to set is the product type. Remember, we have level 1B products, which you can see here, and level 2 products in Sentinel 5P. Today, we are interested on the level 2 NO2 product, so let's select it. Here we could select level 2, and we could select also the timeliness, but those are redundant parameters that are not helping us to reduce the results. So the only thing you have to set is the level 2. Of course, in the product type, it is already implied that it is a level 2 product. So that's fine. So once you have your parameters, do not forget to log in, by the way, into the hub. Remember, Copernicus data is free and open, but you have to be registered. It is free and very quick in order to get the data. So I already logged in, and now let's just run the search. Okay, so here I have my result. In total, 36 products were identified. And as you can see, when downloading level 2 products that are offline, and you can see they are offline here on their name, you can see we are getting the full orbit. So if I select, if you see the product being highlighted on the map, you see we get the complete data set of the orbit. It's not a subset like in other Sentinel missions or like with near real-time products of Sentinel 5P. Again, we will see this difference later on the exercise. So once you have identified the product of interest, in our case, we want the 36 products in total, so we want all of them. You just have to download them. And how to do that? Well, you can just, for example, click on this arrow here, which will start the download process. You can just save it. And as you can see, the download process starts in my virtual machine and the data gets downloaded. Of course, since we are looking for 36 images for 2020, and I can tell you all the 36 images for 2019, you can imagine the download process is kind of time consuming because you would have to click several times here. So here are several solutions. You can automatize the data download process in different ways. I will not cover that in this training session as this would make us run out of time, but there are options for that. Anyway, for this exercise, we have downloaded the data in advance for you. So actually, you don't have to go through the data download process. I just wanted to show it to you so that to make sure that you know how to do it. Okay, I'm going to close my browser now, and I want to show you the folder that we are going to use to run this exercise. So within the RUS VM, we can open the file manager, and within the folders of the VM, you have to go to a specific one that's located in this specific path. It is shared training SALS 0620, so June 2020, then monitoring pollution Spain. This is the path in which I have placed all the relevant files that belong to this exercise. And I want to give you a very brief overview. As you can see, we have 3 folders: aux data, original, and processing. And it is not very hard to imagine what they contain. In the original folder, we will see the original files, so all the Sentinel 5P data that we will be using today. And as you can see, we have the images for starting on 2019. So I have here my data set that goes until here. So from the 15th of March 2019, and the last one belongs to the 31st March 2019, and then the same thing applies for 2020. So you can see here my data set. In addition, I have an extra product, which is a near real-time product. And I have it just to show you later on the exercise difference between a level 2 NO2 NRT product and a level 2 NO2 offline product. Okay, so that's my original folder. Then I have my auxiliary data. So as you can imagine here, I have extra files that I need to run my exercise. And then in the processing folder, I will place all the outputs that I will be creating during the analysis. Okay, so once this is clear, we can now start our exercise. And for that, I'm going to open Jupyter Lab. And I'm going to open Jupyter Lab within Anaconda environment. So let me give you a very brief overview of what Anaconda, Python, Jupyter is, so that we are all in the same page. Well, Anaconda is a free and open source distribution of the Python and R programming languages for scientific computing, and it aims to simplify package management and deployment. So Anaconda is just a distribution of Python and R. You could install Python in your virtual machine by directly downloading, let's say, the Python programming language. But Anaconda gives you a framework in which you can handle all the dependencies and the libraries and the packages in an easier way. So it is very convenient, and I just recommend it. Of course, it's not the only way, but it's the one I will be using today. So let me launch. Okay, so that's Anaconda. And then we have the Jupyter Notebook. So the Jupyter Notebook is an open source web application that allows you to create and share documents that contain live code, equations, visualizations, and so on. So let me first open the notebook, and then I will explain you while you see it. I think it's going to be easier. So in my RUS Copernicus virtual machine, I'm going to open the terminal, and from the terminal, I'm going to access a specific Conda environment in which I have all my Python modules installed. I have called this environment RUS, so I will just use Conda activate RUS. And within this environment, I'm going to launch a specific software that's known as Jupyter Lab. Jupyter Lab is just the evolution of the Jupyter Notebook project. So as I was saying, the Jupyter Notebook or the Jupyter Lab, let's talk about Jupyter Lab to avoid confusion. The Jupyter Lab is, as I said, an open source web application. So as you can see, it is open in my web browser that will allow you to combine code, in this case Python code, with rich elements such as text, paragraph, images, and so on. So within the Jupyter Lab interface, I need to access the specific script that I have created for this exercise. Remember, you will not be asked to write any Python code in this specific exercise. You are just asked to follow the exercise, to understand the steps, and then try to repeat it by yourself and potentially adapt it to your own study area, for example. So within the Jupyter Lab, I'm going to access a specific folder. In this case, I'm accessing the folder of the exercise that I have mentioned before. And I can do so by opening the browser, the file browser within Jupyter Lab. And by navigating to the folder of my exercise, I go to the aux data folder. And in here, I'm just going to open the Jupyter Notebook that I will be using in this exercise. So here it is. I'm just going to close this and to close this. And now, just to make it more visible, I'm going to do full screen in my browser. Okay. So here we have it. This is the Jupyter Notebook. And as you can see, it contains rich elements. We have images, we have code. Sorry, we have images, we have regular text, but we also have Python code. So remember, notebook documents contain both computer code, like Python, and rich elements like paragraphs and images and so on. And the good thing is that notebook documents are both human readable, and they are also executable documents that you can use to run and perform your analysis. So let's get started. Since we have gone through the slides before, sorry, we don't need to go through the text. This is just an introduction to the exercise and to the structure of the exercise and so on. It's basically the same as I have explained before. So let's go. Well, the first thing we have to do in this exercise, and we're working in Python in general, is to load our Python modules. Those are the specific toolboxes, let's say, that contain the algorithms that will allow us to process the data. And as you can see, well, we have a long list, but I want to highlight here a small detail that for those of you that are already familiar with Python, it's very obvious, but for those of you that are new to Python, I think it's important. As you can see, to import a library in Python, we use the import keyword, let's say, followed by the name of the module, in this case, xarray. Remember, xarray is the main library we will be using today to process the netcdf files of Sentinel 5P. So import xarray, and as you can see later on, I'm putting as xr. Here I'm creating an acronym so that later on in my code, I can call this specific module by writing xr instead of xarray. This is just to make the code simpler. And this is kind of standard procedure in Python. Some very well-known libraries, such as NumPy, are usually imported with a specific acronym, such as NP. For example, the Pandas library, which is also very well-known, it's usually imported as PD. Of course, you can just put the acronym you want, but I would recommend you to try to follow, let's say, standards or conventions, let's say. It's not that it's written anywhere, but it's usually done. Okay. So let's start the exercise, and just want to show you the slide here. So we have done the point 1, the download of Sentinel 5P. I have introduced you already to Python and Jupyter and Anaconda. And now we are going to focus on point 3. I will show you how to take one single Sentinel 5P level 2 product and just play with it a little bit. Okay, so again, do not worry about the text. This is just the same as I have explained before. The thing I want to highlight here is that we are going to take a single file, and basically we are going to explore this file structure that we can see on this image. We will be checking the global attributes, and we will accessing the different groups, and then we will go until we reach the actual variable, the actual geophysical parameter that was measured or that was retrieved from the measurements of Sentinel 5P. Okay, oh, it seems here I have a little mistake here. Okay, let's move on, doesn't matter. Okay, so the first thing I'm going to do is, well, so first of all, let me tell you, the objective here today is not to focus on the Python script and really see every small detail, every single character. Of course, I'm going to explain you the code, and I want you to understand it even if you are a beginner. But I will not be spending time into going to every single keyword, parameter, and syntax. Okay, so the first thing, let's get started, is to say to Python in which folder we have the products we want to highlight. And as you can see, this is something that I'm doing here. I'm creating a Python variable that is called product path. And I'm saying, okay, in this specific path of my virtual machine, of my RUS VM, which is the exercise folder, I have my original data. And then I'm saying, okay, I want to create a list. So I'm going to create another Python variable called input file off for the offline products, remember? I'm going to create a list that will contain the path to those files, and then a second list that will contain the path to the specific near real-time product that I want to show you in this part of the exercise. Then I'm just printing a summary of this information with these 2 lines here, and then I will just create a new Python variable that is going to be called s5p_file that will be pointing to the first element of my list that contains the paths to the near real-time products. So let's run this and let's see. Oh, sorry, I got an error, of course. I forgot to run my previous code cell in which I import my models. So let me just do this. Okay, there we go. As you can see, we get the confirmation message. Everything is running fine. So let's just run now this one and now. Okay, so as you can see, in my folder that I have defined here, I have 69 products that are offline, and I have one single product that is a near real-time product. Of course, this first part of the exercise is going to focus on this specific file, and we are going to have a look together. As you can see here, I just have a confirmation message telling me that the product that we are going to analyze now is the one stored in this specific path. Okay. So let's move on and let's see what we're going to do now. So once we have the data, once we have identified the product and its path, its location in the VM, I'm going to open it with the xarray library. You can see here xr for xarray, and then I'm calling a specific function open dataset, and I'm pointing to the s5p file variable. So I'm going to open this file and I'm going to save it in a Python variable called s5p_img_ga for global attributes. This way of opening the netcf file in Python will give us access to the global attributes of the file. Remember, to this root level of the Sentinel 5P structure. Then I will just use a small modification of the same code. I will just write xr open dataset Sentinel 5P file, but then I'm going to add the keyword group. You can see it here. And then I'm saying I want to access within the netcf file structure. I want to go into the metadata group, and more in particular, I want to go into a subgroup within metadata that is known as granular description. This is just a subgroup that contains metadata information, one of the subgroups. And then I'm just going to do the same, but in this case, I'm going to focus on the product group, which is the one that actually contains the geophysical parameter. So as you can see, I'm doing everything in one code cell. And after accessing the different parts I said, I'm just printing them here to have a look once I run the cell. So let's run the cell and let's see the output. Well, first of all, we have the global attributes. As you can see, metadata information. We have no dimensions for this at this level. We only have attributes. Remember from my slide, attributes in netcf files are metadata. Remember this slide here? So attributes, metadata, let's go back. And as you can see, what kind of metadata can we see? Well, the institution that was in charge of this product, KNMI in the Netherlands, well, the creator email, if you're interested in that, and so on. Again, a full description of the meaning of those metadata, you can find it in the product user manual. Okay, the next thing we did was to access a specific group, the metadata granular description. And as you can see, we can access more metadata information, in this case, the processing level, processing node, and so on. But finally, we reached the product group. I told you this was the important one, the relevant one. And as you can see now, we have dimensions, coordinates, and variables. And once we access a variable, we will see the attributes. So we have, let's say, the full structure of the netcf file that I was mentioning on my slide. We can see it here. Okay, so now the question is, okay, we can see the data here. We have accessed the product group, but I mean, apart from this, it's not very visual. We don't see the data by itself, right? So the next question that comes immediately is, how can I access one of those variables that contain the actual measurement, the actual, I mean, not measurement, but the actual geophysical parameter, in this case, the NO2 concentrations? Well, that's a valid question, and that's why I have it right here in my next code. Whenever you want to access a netcf variable in a Sentinel 5P product, what you have to do is the following. First of all, I'm creating a new Python variable called NO2, and then I am pointing to the Sentinel 5P image product group that I have opened before. So basically, I'm pointing to this. And with the syntax of opening a bracket and just putting in quotation the name of the variable I want to access, then you have the job done. Remember, so you can see basically I want to access the nitrogen tropospheric column, which is this one here, because this is the one that contains, this is the variable that contains my the information I am interested on. If you want to know the definition of the different variables, again, go to the product user manual document and you will see it there. So I'm opening it, and then I'm just writing its dimensions, coordinates, attributes, and in this case, the values of the variable. Well, so here we can see the geophysical parameter. We can see its dimensions within the netcf file structure. We can see the coordinates. We can see the attributes. Remember the metadata of this variable. For example, the units of the variable, which is mole per square meter, the standard name, and so on. And then we can see the actual measurement. And as you can see, if you are familiar with Python, this is basically a NumPy array. So it's just, let's say, it's an array that contains the values. And this is the actual measurement. This is what we need to start running our analysis. But of course, this is not the best way to represent the data. It doesn't look very, not very nice, just numbers. So of course, the question is, how can I plot this to see an image out of that? Well, let's have a look. Actually, the first thing I want to show you is that within the variable here, within the NO2 variable that we have opened, there is a specific attribute that is called multiplication factor to convert to molecules per square centimeter. And then we have a number. Well, this has a specific reason. And what is that? Well, the units that are used to represent the biophysical parameter in Sentinel 5P follow this international system, the international system for units, so SI. However, in this specific domain, or in this specific scientific domain, usually, so the international units are mole per square meter. But in, as you can see in the text here, in this specific scientific domain, usually molecules per square meter are the units that are used for the analysis. So luckily, the Sentinel 5P level 2 product contains already the multiplication factor to move from one units from these SI units to, let's say, the more well-known units used in this scientific domain. So before plotting our variable, what we are going to do is to change to convert our measurements to the, instead of being mole per square meter, to molecule per square centimeter. And how do we do that? It's very easy. We are, again, calling the NO2 variable. So we are going to overwrite our variable, and we are saying NO2 should be equal to NO2 multiplied by the multiplication factor. So this is basically what's happening here. So once this is done, we are just ready to have a first visualization of our product, and let's have a look. So here we have the product, and if this is the first time you look at the Sentinel 5P product, you can see that it has a very large swath. Remember, it's 2600. So you can see on the axis the lat and lon coordinates. So this is 0 in longitude. So of course, looking at this data without knowing or without having a geographical context is not very useful. So one could argue that a better visualization should be made. And actually, I agree. So what I want to show you in the following code is how to improve the visualization of this single file. As you can see, this is a near real-time product, and it is because of that we do not have the full orbit. So let's improve the visualization. Here, for improving the visualization, I'm using a specific Python library that is called CartoPy, which I recommend you to check if you are working with this data. It has its main ability is that it allows you to plot data using specific projections, and I think it is a very nice one, a very nice way of plotting the data, especially when working with satellite imagery, in the case of Sentinel 5P. So I don't want to go too much into the details of the code, but I want to give you a few details, a few key information. First of all, let me just run the cell, and let's see the output. By the way, apart from plotting the image, I'm also saving it directly into the virtual machine. So the plot you can see here is automatically saved as a PNG image into your VM so that you can then share it with your colleagues or include it in your reports and so on. So as you can see in this visualization, what I have done is I have projected my data into the orthographic projection. And then I have added few things. For example, I have added the main rivers. So you can see, I mean, it's sometimes nice to see. I have also added a specific title, and I have added the coastline so that we can better locate the product and where it is overlapping. As you can see, it is a product that is covering the north of Africa, of course, Spain, Italy, France, Germany, Denmark, well, I mean, and so on. So as you can see, I have also added a text, in this case, Madrid, but of course you could add all the texts. You can see that in terms of concentration, there is definitely a hotspot in Spain, which is in Madrid. We have all the hotspots in the north of Africa, but I would say the part that is taking all the attention is definitely the north of Europe, right? We can see here, compared to the rest, there is a huge concentration. And this is usually the case in the north of Europe. The concentrations are usually higher. Okay, there are a few things you can do. I mean, there are some things you can do to even to modify this plot. For example, instead of zooming into the extent of the product, we could uncomment this line, which is going to set the zoom of the plot to a global scale. But also we can add a specific image as a background, and you will see now later once I run it again. And I'm also adding the grid lines to just locate in terms of lat and lon the location of the product. So let's so basically I'm just adding these 3 specific lines, and let's see the result of that. Okay, so here it comes, and as you can see, now I have my product, let's say, zoomed out. We can see the effect of using an orthographic projection. We have this kind of 3D spherical shape, very badly described, but okay. If you want to change the projection, I recommend you to check the CartoPy documentation. There are many more, some of them are very nice, and I would say it's fun to just play a little bit and produce different outputs. As you can see, I have added also a stock image just to give more context, and I've also added the grid lines. So as you can see, this is just to show you the flexibility you have in Python to create nice plots. I mean, it's not a GIS environment or a graphical software, but if you have the right code, you can produce very nice visualizations of your data. Okay, so we have opened a single product in in Python from Sentinel 5P. We have played with it a little bit, but now comes 2 of the main tasks that you should do when working with Sentinel 5P data. The first one is what it's called the filtering of the data to remove the bad quality filters. So let me give you here a brief summary. So the quality of the individual observations depends on many factors in the case of Sentinel-5P observations. And this includes, for example, the cloud cover, the surface albedo, the presence of snow, ice, the saturation, the geometry, etc. Those are parameters that can affect to the quality of the final measurement that is done by the satellite. So these aspects are taken into account in the definition of the quality assurance value, also known as QA value. And this value is available for each individual observation, meaning for each individual pixel. And this provides the users with an easy filter to remove less accurate observations. So the QA value is a continuous variable ranging from 0, which is a complete failure of the pixel, to 1, meaning perfect quality. And in order to use this filter, you should follow this following recommendation. Again, this recommendation comes from the technical documents of the product. Again, as you can see, I recommend you to check them again if you want to know more. So usually there are 2 thresholds that are defined. First of all, 0.75. And as you can see on the Jupyter notebook, this is the recommended pixel filter. It removes cloud cover scenes, partially snow ice cover scenes, and errors or problematic retrievals. Then we have a lower threshold, which is 0.5. And compared to the stricter filter of 0.75, this adds the good quality retrievals over clouds that can still happen, and also over scenes that are covered by snow and ice. So in particular, this filter might be useful for assimilation and model comparison studies, but for single data analysis, it's recommended to use 0.75. And this is why we are going to use it in our analysis. So how to filter a Sentinel-5P product to remove bad quality pixel is very easy. We do it in this line. As you can see, I am creating a Python variable known as NO2_filter. And then I'm saying to my NO2 variable, so to the NO2 product, I want to use the where function of the X-array library. And I want to say in the Sentinel-5P product, you have to, let's say we are telling the computer, access the QA value, and wherever this QA value is larger than 0.75, keep that pixel, and if it's not, just drop it, remove it. And then once this is done, we are just here plotting everything to have a look. So let's plot it. Again, we are automatically saving this plot that is going to pop up now into our virtual machine so that we can share it and use it for our reports. So what can we see here? Well, on the left side, we can see the quality values, so the quality flags. And as you can see, it is quite rather a good quality product. We see the values they ran. I'm looking at the left side from 0 to 1, so bad to good quality. And most of them have a quite high quality, which is good. We have some green values here, which are more or less in the edge of the threshold. On the right side, we can see the effect of this filter, and we can see how easy it is to remove those bad quality pixels. We can see, for example, almost all Italy, part of Italy completely went out. Spain is doing well here. We have the area covered pretty much. Also in the north of Europe here, this area that is definitely a hotspot, we have the good quality measurement, so this is good. So what I want to tell you is when processing Sentinel-5P data, you have to remove bad quality pixels. This is fundamental to account for distortions that can happen in the observation. And in this way, you can do it, as you can see, very easy. Okay, a second task that I think is very common for any user is doing a subset. How to do a subset if I want to just focus, for example, in Madrid, the capital of Spain. Well, this is very easy. And let me show you to you. First of all, I am defining a specific region of interest with the lat-long coordinates. So I'm defining the upper right lat-long coordinates of my region of interest for the subset, and the same for the lower left coordinates. And then again, I'm creating a new variable, in this case, NO2 subset. And I'm saying I want to filter, I want to use a starting point, the filtered product. So I want to work with this one here, the one we just filtered. And again, using the where function of the Xarray library, I'm going to say wherever the longitude of the filtered product is smaller than the upper right corner longitude, and then the same, but in this case, wherever the filtered product has a longitude that is compared to the lower left corner larger, then I want to filter the data, and then basically we do the same for the latitude. So it's just a basic comparison, smaller or bigger than my region of interest. So with this single line, we do the subset, and then basically here, I'm just plotting the result. Again, I'm not going into the plotting code. I don't think it is very relevant. Of course, you can play with it. You can read more about it. But I think the important part here is how to do the subset, actually. So this is the line that is doing the work. Let me see if I can select it. And this is the thing you have to know. Okay, again, I'm plotting, I'm setting automatically the result, and let's run it. So here we see the result. We see, well, the subset we have done, it's covering the region of Madrid, and we can see a clear hotspot in the city. Okay, so once this is done, let's now move to the second part of the exercise. So remember in my slides, we are here. So we have done point 1, 2, and 3. Now we are going to move to point 4. It is here where we are going to actually do the multi-temporal analysis to derive the average concentration of NO2 in mid-March 2019 compared to mid-March 2020. So let's go. Let me go back again. Okay. And let me introduce this part of the exercise to you. So the first thing I want to tell you is about HARP. HARP is the main driver, the software we are going to use to run this part of the exercise. So HARP, as I said at the beginning of my slides, is part of the ESA Atmospheric Toolbox project and aims to provide scientists with tools for ingesting, processing, and analyzing atmospheric remote sensing data. The ESA Atmospheric Toolbox project consists of several components, which, with the main ones being CODA, HARP, and VSEN. And these components are made available by means of several software packages. You can find more information on the ESA Atmospheric Toolbox website that I really recommend you to check. So more in concrete, HARP is a toolkit for ingesting, processing, and intercomparing satellite data or model data against correlative data. So the toolset, and this is very important, provides a set of command line tools, a library of analysis functions, and direct import-export interfaces for Python, IDL, and MATLAB. So it is then HARP, a command line, is a set of command line tools, and we are using an interface in Python to run our analysis. What I mean by that is that you can use HARP directly from command line or via MATLAB or via any other programming language that has an interface or that can call terminal commands directly. So what we are going to do is we will use the HARP toolbox to generate level 2 products from the original level 2 Sentinel-5P data. So what is this conversion from level 2 to level 3? Well, due to the characteristics of the sensor and due to the wide swath and so on, we have data that do not follow a common spatial grid over the complete swath. So in order to compare data in order to run multi-temporal analysis, we have to make sure that we move our data set into a common spatial grid in order to have the same pixel size all over the region and then be able to add those pixels to do average concentrations, minimum concentrations, and so on. So this is the main thing we are going to do with HARP. And how to do so? Well, let's go through the code. The first thing I'm going to do is define a variable that is going to point to the path in my virtual machine in which I want to save the output of this conversion. So I have my input level 2, I'm going to create level 3, and I want to store these level 3 files somewhere. And as you can see, I'm going to do it, I'm going to save them in this specific folder. if you can see, you can recognize this is the exercise folder, and I'm just pointing into the processing subfolder. Okay, then comes the relevant part here. In order to define the common spatial grid that will be used to resample our data from level 2 into level 3, so to resample the original data into the original grid, we're going to transfer to the resample one that has a regular grid. We need to create this grid. And think about the grid as an empty raster. When you create a grid or an empty raster, you have to define the resolution of the raster and the extent, so the position of the raster in the map, right? So its original coordinates, the lower left corner, the upper right corner, and so on. So in this case, I'm creating a variable that is going to be called step, and the step variable will define the resolution of my grid, of my, let's say, empty raster, if that makes more sense for you. In this case, I'm setting the resolution to 0.01. This is not meters or so on, this is degrees. Then I'm defining the coordinates, the location of my grid, of my empty raster, and I'm doing so by defining the lat-long coordinates of the lower left coordinate and the upper right coordinate. So as you can see now, I have, in an abstract way, I have the points to create my grid, and I also have the resolution that I want to put in that grid. Okay, so once, let's say this is done, and you can see it here in these first 3 lines, I'm going to set 3 extra parameters that have to do with the way HARP works. First of all, I am creating a variable that I'm going to call lat edge offset, which is going to point to the latitude of my lower left corner. So this is just a duplicate, and then I'm creating the variable long edge offset, which is pointing to the longitude of my lower left corner of this grid. Then, in order to define the grid, instead of setting the upper right lat and long coordinates, this in HARP has to be done in a different way. We have to provide, instead of the lat long coordinates of the grid, we have to provide the lower left coordinates in lat and long, and then its length, both in terms of latitude and longitude. So here we are creating the length in the latitude and longitude direction with a very small trick. I'm taking the latitude of the upper right corner, I'm subtracting the latitude of the lower left coordinate, and then I'm just dividing by the resolution. This will give me the length of my grid, and then the same for the longitude. So pretty basic operation. So once this is done, I'm just going to print the result of that to have a look. And then I'm creating here the set of operations that I need to transform my data from level 2 to level 3. So let me first run this code cell, and later on I will explain you one by one these operations, which are very important to understand. So first of all, I'm just going to create my export path variable, and then I run this one. So as you can see, I have my lower left latitude coordinate is this one, and it has a length of 8.41 degrees. Then in terms of longitude, I am starting at minus 10.99 in terms of longitude for the lower left corner, and its length towards the longitude direction is of 15.67. So as you can see, this is just the result of this code here. So once we have defined the, so far we have only defined the parameters to create the grid, but we haven't done the conversion from level 2 to level 3 yet. And this is going to happen next. What we are going to do is, and I'm moving here to this code, and later on I will explain you this part. What I'm going here is, okay, let's not go into all the code, not to lose the focus. What I'm doing is I'm using the HARP library here. So I'm calling HARP, and I'm saying with the import product function of HARP, which is going to allow me to ingest the netcf file from the virtual machine into Python. So I'm calling the import product function of HARP, and I am ingesting I, which in this case is, I am in a loop, so I is just pointing to every single of those original data that I have. So if you remember in my VM, I showed you the original folder here. So I'm saying, take every single one of those files and open it in Python with the right function. So every single one of those, as you can see, it's kind of a heavy task. So I'm saying, take every single one and then apply a set of operations that I'm going to explain to you now. Once this is done and the conversion is done, I'm just exporting the output into the processing folder, and I'm saving it as a netcdf file, the level 3 product deconversion. So the rest of the code here is just doing that basically with some exceptions in case there's an error and so on, but that's not the important part. What I want to understand, what I want to try to explain is the set of operations that are required to move from level 2 to level 3. And these operations that I was mentioning here, that we are going to apply to every single file that we have as original level 2, is defined here. So what's happening? First of all, we are taking our data, and once it is ingested by HARP, we are saying, filter out the products which have a quality value that is smaller than 75. So the same thing we did before. In this case, instead of using the Xarray syntax, we are using the specific HARP syntax that is needed. In this case, you can see this has to be specified like that. Once the pixels are filtered, the bad quality pixels are filtered, I'm going to transform the units into molecules per square centimeter instead of mole per square meter. This is not mandatory. I mean, it's up to you to choose the units you want, but just to show you how this is done. For that, we are using a specific function in HARP that is called derive. And again, if you want to know more about this, I would recommend you to check the documentation of the HARP software, which contains a very detailed information about all this. So I'm using the derive operation to derive the units in molecule per square centimeter. Then I am using again the derive operation to create a new variable in my product that is going to be called date time stop. And this will just give me information about the stop sensing time of the product. It's just for redundancy, but it's good to know. Then comes two key steps in the processing of level 2 to level 3. First of all, we are doing a subset in this line here. So what we are doing is basically saying, wherever the latitude is larger than my lat edge offset, so this variable here, then we're saying together with a latitude that is smaller than my upper right corner in latitude, and the same for the longitude, then we are saying wherever is within these boundaries that I'm defining, it has to be kept in my output product, and the rest has to be just masked out. So it's just a subset. The only tricky thing here is the way the subset is created, but it's easy to understand. It's a subset. Then comes, I would say, the most important part, which is the bin spatial operation. In this line here is where the transition from the original grid to the common grid with common resolution and extent and so on is going to happen. And it is a little bit confusing, but let me explain it to you step by step. As you can see, I'm calling the bin spatial tool of HARP, which is going to do the following. As you can see, I have here I have 6 variables in brackets. I have 3 for the latitude, so lat length, lat edge offset, and step, and then 3 for longitude, long length, long edge offset, and step. Let me explain you how this works for the latitude, and then the same applies for the longitude. So I have here my variables for the latitude, and it is in this way that you have to define the grid. You have to take as reference always the lower left corner. So the first thing we are doing is what we are defining in this variable lat length, the latitude coordinate of the lower left corner of my new spatial grid. Remember, this lat length is defined here. Sorry, I think I explained it in the other way. Here we are not defining the lower left corner. We are not defining the latitude of the lower left corner. This is done here in the second position of my string. So lat edge offset is telling me the latitude coordinate of my lower left corner of the grid. Then I'm saying the grid has to start in this coordinate and has to have an extent that is defined by the length in the latitude direction. And remember, the length we have defined it before here. And then we are saying that this length should be divided with a specific resolution that we define with the step variable that we did here, 0.01. So as you can see, it's a little bit tricky. We first establish the length, the lower left latitude, and the resolution, and then we just do the same for the longitude. Again, if you have questions about this, of course, feel free to ask me if it's not clear. But if not, I would recommend you to check the technical documentation of HARP. There are different ways to define the grid. It's not the only one, but I think in this way, it's easy to understand. Okay, so once we have defined the spatial, the common grid, we are just deriving the coordinates of the central coordinates of every pixel. This is just an operation that is required because the beam spatial operation, and I'm saying this as a side note, it's not very important. The beam spatial operation will not give you the central coordinates of every pixel. And some softwares usually work with this assumption. So in order to make sure that this is present on the data, we derive it here. And finally, we are just doing a band subset. We are telling that from the original level 2 product, we want to keep, and that's why we use the keep harp function, some of the variables that are contained in the original level 2 netcf file. And here we just specify their name. So this is the list of operations that are required to move from level 2 to level 3. You can see here level 2, level 3 operations. And remember, we define them here. And in this code cell, it's where the conversion will happen. Again, I remind you, we import the product, we pre-process it, and then we just save the output as a netcdf file in a specific folder. So this part of the exercise takes some time. The processing takes around 20 minutes or so. And of course, we don't have time to do so. So I have run the analysis in advance. This specific code cell has the ability to detect that the products have been already processed. So if you run it accidentally and the products are already in your processing folder, it will not run. And I want to demonstrate you this here. In my exercise folder, if I go to the processing folder, you see I have the data already converted into level 3. And you can see it is level 3 because I have in the name, I have in the name Sentinel 5P underscore offline underscore level 3. And before it was level 2, right? Okay, so let's go back to the Jupyter Notebook. So if I run this cell, basically what's happening is that no processing is done because it was already done in advance and it's telling me that. So it went very fast, obviously, and it's telling me 69 out of 69 products, level 2 products were converted to level 3. In case any error would happen, then an exception or the file would have been stored in this specific variable. In this case, they all were successful. Okay, so once we have our data converted into level 3, we are almost at the end of the exercise. The only thing we miss is to derive the average concentration over our study area, in this case, Spain. So what we are going to do is, again, import the data, the level 3 data, from the files that we have on the VM into Python. And how do we do that? It's very easy. First of all, we create a list again that contains the path to all those files. And then I am using, again, xarray. So you can see it here, xr. I'm using a specific function to open a list of files, which is called openmf dataset. And then I'm just providing the list of files that I want to open. As you can see, I'm also saying that I want to combine the files together with the nested keyword. This is basically going to create a stack of files. So, you know, raster stacks it's a very common structure that facilitates the data processing. In this case, netcdf files can also be stacked. And for that, we use the combine keyword. And to combine and to stack the products, we are going to use the time dimension, so that we use the time information of the products to create the stack. So there's also a small detail I want to mention here, is that since we are using the time dimension to stack the products, we need to make sure that the time dimension of every single product is seen by Python as time information. It's not the same having a string with a date than having a date time structure in Python, because the manipulation of the data, I mean, if you have the correct structuring in terms of date time information, you will be allowed to do time manipulation on your data. If it's just a string, a text, then you will not. And to make sure this happens, we are here creating a small function that will first of all read the date time start attribute of every single file, and it will read it as a pandas to date time format. So we run this cell, and what we can see is the output. Again, we see an overview of the stack netcdf file that we have created. As you can see, we have 69 products in the time dimension, so we have stacked them together. And they all share some specific variables that we defined in HARP before, and so on. Of course, they all now have a common grid, and that's why we can merge them together and do average concentrations and so on. Okay. The next thing we are going to do once we have the files imported into Python and stacked together is we are going to do a subset, but not a regular subset. We are going to crop them using a shapefile. Again, and since we are running a long exercise, I don't want to go too much into how to crop netcdf files with a shapefile. I want just to point it out. I mean, you have the code, so you can do it by yourself. Just want to point out that there is not a native solution for this, so you need some tricks. In this case, we are creating a specific function. We are taking a shapefile, in this case, a shapefile of the borders of Spain to run the analysis. Again, if you have questions about this, feel free to ask me, but I don't want to lose time in this in explaining this code, because it's not the relevant part of this exercise. So what we are doing is cropping the netcdf files with our shapefile, which will give them the shape of Spain, basically, of our region of interest, in case it changes. And once this is done, we are almost at the end. So our data set is formed by images from mid-March, the second half of March 2019, and the second half of March 2020. So in order to compare the results in both periods, what we are going to do is split the data set into one for 2019 and one for 2020. And this is basically what we are doing here. As you can see, I'm taking my level 3 products and I'm saying I want to cut them, I want to slice them, let's say, using these specific dates. And as you can see, this is why it is very important to have in Python the time information as as a format that is seen by Python as time, because this will allow you to run these very basic operations in a very easy way. So I split my data set for the one of March 2019 and the one of March 2020 here. And then I'm just going to do a simple task that will make sure that I have only one measurement per day. If you remember from my slides, Sentinel-5P has a daily global coverage. So one image, let's say one product per day. However, due to the overlap of the orbits, it might happen that in some regions you can have two observations per day because of this overlap. However, to run our average map, what we want to do is to keep one single measurement per day and then average that over the period, right? So what we are doing is whenever the system will see that I have 2 files per day, I will derive the average concentration for that day and then use that as an input for my upcoming average monthly average map. So this is what I do here for 2019, and the same I will do for 2020. So if we run this, now we can see that we have our datasets that are that have 17. So if you remember before, I had 69 images from 15th of March to the 31st of March in 2019 and 2020. But of course, if you reduce that to one single measurement per day, you end up having 17. So 17, and then you can see they start on the 15th of March 2019, and the last one is here, and then for 2020. So those are two separate data sets that you are seeing here. And now we only need to average all the values together. So we do it for 2019 and for 2020. So we derive the mean, and once we derive the mean, I'm going to specifically select the tropospheric NO2 column, which is the variable of our interest, to create the final variable that will be called NO2 March 19 mean and NO2 March 20 mean. So let's do so. Once we have the average concentration performed, we can now display the result. Since we have two data sets, one for 2019 and one for 2020, I'm giving you here the option to select the one you want to show. I'm going to show you both. So let's start by displaying the 2019 results. So I'm just going to run this cell, and in the end, this very long code cell is going to do the plot. Again, let's not focus on what's happening here exactly, because it's not important. Of course, if you're interested, let me know and we can have a look later, but for the exercise, I want to keep it simple. So let's plot the result and let's have a look. Okay, so it takes a few more seconds and we will see it now. Okay, while it comes, okay, here it is. But anyway, I want to again highlight the fact that we are saving the files automatically as a PNG file. So the plot is being saved as a PNG file. So that's good to know. Okay, so here we get the final result. And as you can see, we get to see the concentrations, the average NO2 concentrations from the 15th of March 2019 until the 31st March 2019. As you can see, well, there's definitely a hotspot in Madrid. This is, if you're not familiar with Spain, this is Madrid over here. There's also a main hotspot in Barcelona, which is the second main city of Spain. And also we can see some hotspots in other major cities of the country. For example, this is Sevilla, this is Granada. We have also over the coast of Valencia some hotspots as well in the north and so on. We can even see some other cities, and I get what I understand as the main connections between them. So I think a very interesting result. Those were the concentrations derived by Sentinel-5P for 2019. But of course, we want to see the effect of the lockdown that was caused by the COVID outbreak in the second half of March 2020. So since we have done the analysis, this is basically the purpose of the exercise, let's now see the results for that. To see the results of 2020, we just need to point to the right variable here. So I'm going to change this to 2020 and just run it again. And we can see now the results. So again, it's taking a few seconds and we can see together the final result. Okay, here it is. As you can see, the graph changes automatically. It's, or at least, yeah, sorry, I was just confused. So the graph changes automatically the time information. So here we are seeing the average NO2 concentrations from the 15th of March 2020 in this case to the 31st March 2020. And as you can see, we still see some hotspots over Madrid and Barcelona, also in some cities in the north, but the values have dropped dramatically if you compare both images. Of course, this is basically the final part of the exercise, the final result, and I want to just show you in a very interactive way the comparison. So what I have done is I've taken those two images and I have created a GIF in Python. This is very easy. You can do it with this code here. I'm just telling, okay, here are my images in this line, and just create a GIF. But, I mean, let's not focus on that, it's not relevant. And here we can see the result. So as you can see, Jupyter Notebook is very flexible in terms that it can run Python code, visualize a GIF, a video. I mean, that's why I think it's a very nice tool to process data and share this processing with others. So as you can see, well, the drop in the concentration of NO2 all over Spain, especially in the main hotspots, is very clear. The case of Madrid and Barcelona are very clear. Also, if you see the main cities here in the south, like Granada and Sevilla, we see a drop as well, and so on. So also a side note, this is the color palette I have used, but of course you can change that very easily. For example, here I used other colors to show the difference. So again, this is just to show you that Python is very flexible. You can manipulate your visualizations in a lot of ways if you know how to do it, of course. And well, this is then the end of the exercise. So I will then put here an end to this part of the exercise. Let me go back to my slides. And I just want to share with you some final thoughts on what we have done. So with the new Sentinel satellites, the challenge in remote sensing is no longer the availability of data, but rather how to store and process all the information. In addition to that, it is necessary to explain how the data can be used and support users in their applications. And because of that, the RUS Copernicus service is here to solve those problems by providing virtual machines to store and process the data, and by offering a dedicated help desk supported by a team of remote sensing experts to help you in your projects with Sentinel data. So this is all I wanted to share with you. Now we are going to move to the Q&A session. So please feel free to send your questions via the questions tab, and I will try to do my best and solve all your doubts. Finally, just to tell you the websites of the project, rustraining.eu and ruscopernicus.eu. And of course, we are in social media. So if you want to stay tuned with upcoming training activities, we do webinars, we do, I mean, not now face-to-face due to the current situation, but potentially in the future, maybe. So feel free to follow us in social media if you want to stay updated with our activities. And again, I will now close the exercise so that we can move to the Q&A session. So thank you very much. I hope you have learned something new today about Sentinel 5P, about virtual machines, about Python, and so on. And if you have questions, please feel free to send them to me. Okay, ciao.
Okay, so this puts an end to the exercise. I will pass now the word to Martin to put some final remarks on this session. Martin?
Okay, thank you, Miguel, for this very nice exercise and the illustration of how Sentinel 5P data can be used and the added value of it, especially in these hard times, of course. I really like to thank you for your contribution and for hosting this session and explaining it all very clearly. Well, our program for the Eyes on Earth Roadshow will start again at 1:10. So we will hope that some participants will go into this session. If there's time to answer some questions of the participants for the RUS training, then please feel free to stay in this session. I will leave you now. I thank you for your participation. And Miguel, thanks again for contributing to our roadshow. Thank you very much. Bye-bye.